So following, get it. Continuing our pursuit of understanding of capacitors.
Can we take like a 5-minute break before we start?
Nope.
That was
How about a halftime intermission?
Okay, halftime break. I'll work hard if we do.
Okay, here we go. So stored energy. So what we're looking at is this idea of charging the capacitor. So we're in the process of electrons coming off of here going this way. So what they do is they're presented it from a Ben Franklin point of view. They're saying positive things are coming this way. So it takes work to bring these on here. In my mind, it says it takes work to take an electron off of this plate and move it to this plate. Does that make sense? Certain distance, there's a force times the distance to take it with an electron tweezer and move it there. They don't. They go, the electrons, because of the potential difference, electrons come off of this plate and go this way. Okay, good with that? And that happens until the voltage across this matches the voltage across the battery. Okay, you did know that. Yep. And that's an application of Kirchhoff's loop rule. Okay. So in this arrangement with no resistor, this takes nanoseconds to achieve. So we're going to look at the process within those nanoseconds. They are like speedy little guys. Okay. Okay. So.
No, they have mashed it up that fast.
So the capacitance. So yeah, this is what I was saying. It goes until the voltage of the capacitor matches the voltage of the battery. Okay. So we're now in static equilibrium. Okay. So what we're going to look at is the process before that happens. Okay, so it takes a little bit of energy, a little bit of work to move a certain takes a little bit of work. We'll say dW, a little bit of work. Electric force times distance. Little I don't know what we're gonna do a little bit. No, I mean it would be dx, but that's not what I'm gonna change. So what I'm gonna change is the electric force is the electric field times a little bit of charge. So this is dq times the gap.
The gap across the.
Yeah, this d here. Tim.
Slightly off topic, but is there a way to do this without a battery, using something else?
Another charge capacitor. Something, anything that creates an electric potential difference.
Will we see something like that on the AP test, or will it be a battery?
Battery. Or another capacitor. Okay. So does that make sense? So here's our force times our distance. Okay. This electric field, because the field is constant, times the distance, that's equal to electric potential difference. Okay. So here we could also look at it in terms of the promise of potential energy times the small amount of charge that we're lifting gives us the change in energy. Okay. From capacitors, we know that capacitance is equal to charge over voltage. Okay, so voltage is equal to charge over capacitance. So this right here is what we're substituting in for this. Lowercase q represents the charge in transition, not in dq, but like just some partially charge on the capacitor plate as we're in the process of charging this. Hey, what's the charge on the plate at this point? It's charge on the plate at this point. That's the lowercase q.
Total charge on the plate.
Total charge on the plate at a certain moment in time. Okay, so it's temporarily charged. This is going to, when it is fully developed, it's going to turn into capital Q. That's fully charged. Okay, good with that? So what we're going to do is we're going to integrate this. So this is changing, but this agrees with the little bit of charge that we're changing from one plate to the next. Right with that? Okay. So this measurement is changing. The charge on the plate is changing, but that agrees with the little piece of charge that we are moving. So our limits of integration are from no charge to fully charged. Okay, and we're going to pull out anything constant, which is just 1 over c. We integrate this, it becomes squared, like 1/2 little q squared, and then we plug in capital Q and then 0, and this is what we're left with. So this is where this equation you had last year when we were talking about the energy in a stored capacitor. It's 1/2 Q squared over C. And I said that's an equation. Like, okay, but that's where it comes from. And this is something that you're going to have to be able to reproduce on the AP test and maybe mastering. Okay. Good with that. Okay. So we also have, I am not sure what equation, if any, they give you on the AP test, the equation sheet for charge for the energy stored in a capacitor. But you could also substitute using this equation as a base. You can substitute in here and can get this equation, that equation for the energy. It's the same thing. It's kind of like power with circuits is equal to current times voltage, but we could substitute Ohm's law and say, oh, it's I squared R. And we can do power is equal to voltage squared over resistance. I don't know if you remember that from last year, but those are all the same things. We just substituted Ohm's law. These are the same things as this. We're just using this idea of what definition of capacitance. Okay. I'm hoping one of those three is on the equation sheet. I think it is. Okay. So that's fully charged capacitor. A little foreshadowing here. This expression here is very similar to the spring potential energy, okay, which we will reference when we get to circuits. Circuits. Yep. Okay. So they have this expression, energy density, which is the energy stored in a capacitor for how much volume it takes up. Kind of like, this is more of an engineering type thing, like the size matters, so you want maximum storage energy, potential energy for the amount of volume it takes up. So after doing some substitution of some stuff, you get this expression. So it's epsilon, it's 1/2 the epsilon naught times the electric field squared. So trying to increase that electric field. Okay. And measured in joules per cubic meter, which makes sense for energy over volume. Okay. Good with that. Okay. Halftime.
What? Can we just continue? Can you go back? Can we take our halftime during the passing period?
Okay, here we go. So polarization of insulator due to external, what? No, I'll let you do the passing period. So we've seen this slide before. If you have an external field, this is an insulator. Okay, you have an external field that causes the molecules to polarize. Okay, which causes electric field to be established. So this orange is the external field from this guy. The field created between the dipoles is weaker, but there is some kind of field there. So making the net electric field less than what it was originally. This is inside the insulator. Get to that. I'll review there. All right, so we're going to call the insulator a dielectric. Okay, all dielectrics are insulators. So let's say we stick an insulator or dielectric between the two charged plates of a capacitor. So what we have is, this is our original electric field with nothing in there, it's just a vacuum. Okay. But then we stick in this insulator, what we get is polarization of the molecules inside the insulator, causing an electric field being in opposition to our original, going this way. Good with that. Okay. So the consequence of that, let's see, where am I going here? The consequence of that is the net electric field in here is going to be weaker because of this inserting this dielectric. Good with that?
Does the strength of the counter electric field vary based upon the substance?
Yes. Okay. All right, so we have so here's our control, like nothing in here, and so we've got this surface charge density. Sorry, the electric field is equal to surface charge density over epsilon naught. Okay, we've got this induced or created electric field from the polarization of the molecules. That's a secondary electric field. We're adding those together and we get a field that's weaker than this one, which is what we kind of said, but we're going to explain it from the surface charge density and this dielectric uh, talking about the surface charge density like within here in this area there. Okay. So it's the same thing. Um, yeah, same thing, just a different picture. So we're getting a weaker field here than we are here. Okay. So everything was a little not, little zero, sub-zero, is this idea that there's a vacuum in between. It's kind of like our control group. So we have a capacitance, we have a charge on here, we have a voltage across here. Everything is like, this is our control group. That makes sense, control group, like an experiment. That's what we're starting with, okay? All right, so then we're gonna stick in a dielectric or an insulator. So this capacitor is isolated, so we've charged it. It has a certain amount of charge. We've already connected to the battery, and then we stick in a dielectric. It's isolated, but we just stick this neutral dielectric in. What happens to the voltage across the plates? I'll give you a list of equations to be able to think through. Tell your neighbor. Correct answer is C. Is everybody good with that? The electric field got weaker.
But the electric field gets weaker, but the like charge on the plates doesn't change. Right?
Correct. Right.
So the charge doesn't change, but the voltage changes.
Yes. So what we're saying is, what that means is, it is easier now with the dielectric to take an electron off of here and move it across this distance here.
Like recharge a battery.
Okay. Oh, it's easier to move an electron. We're not going to. Okay. This for me helps with the distance thing. Technically, if well, we'll just leave it like that.
That's okay. Okay.
It's easier now with the dielectric to move an electron from here to here where it doesn't want to go.
What I was thinking was, if the charges are the same, then the voltage can't be different, but it's different because there's something in the middle.
Correct, because the electric field got messed with. It's going to take less force to move that across there. Everybody okay with that? Okay. So what happens to the capacitance? Definitely put equations up to the top here. answer is B. Okay, charge stays the same. Voltage goes down, capacitance goes up. Okay.
Using permittivity constant area over D, how does that A over D, like the other equation for capacitance, how does that one change?
Oh, good question. Hang on to that. We might get to that today, but that's a great question. That's a great question. That is a great question. Okay.
Is that a
Thank you. Okay.
Oh, okay.
So when we have an isolated capacitor, okay, the charge with or without the dielectric stays constant, but our electric field decreases, our voltage decreases, but our capacitance increases because we have the same amount of charge, but for a smaller electric potential difference across the two. Okay.
I'm gonna go refill my water.
Sure was. All right. So, what happens to the energy stored? Correct answer is?
Go up.
Answer is decreases.
Uh-oh.
As the capacitance goes up, energy goes down. Okay.
Yeah, that kind of makes sense.
Now,
Oh, that does make sense.
correct answer is A. Okay, so it polarizes, meaning this is negative, this is positive. Okay, and it's attracted. This is why the energy decreases, because it's doing what it wants to do. If you had to push it in there, it was a repelling that would increase the potential energy. But because it's doing what it wants to do, that's what causes a decrease in energy. That makes sense? I mean, you got to think of like, it doesn't just magically go away. There's something physically that happens. Okay. So now we're changing the scenario. Okay. No, it's a continuation of the story. Sorry. So we're here. We started with this. Then we inserted the dielectric. Okay. So everything we've got, like we have all this, and then we take this scenario here, and we connect that to a battery.
What happens as soon as the battery is connected?
Yep. Like after it reaches a static equilibrium point. So not in the process, but after it's said and done.
In this case, it would be like a couple microseconds at most.
Yep. Have a conversation.
Honestly, we have to
B.
Andy.
Oh, I have to pick multiple.
Well, you don't have to.
Yeah, B happens.
but you might be wrong.
B happens.
You got a question about the voltage. You got a question about the charge.
B and E.
Just change the voltage scale. Field has to increase. The field to increase. The surface has to change, right? But it is for the charge to increase.
What do we say?
Is it B but not E?
Okay, so this B is correct. Okay, loop rule has to be true. Okay, voltage gain has to equal voltage drop. Okay, so this increases until it matches the battery. Okay, and because of that, there's now more charge on the plates. Okay, because the capacitance with the dielectric is now bigger, and we bumped this up, causing more charge. And this is why we have a dielectric between capacitor plates. It's able to hold more charge for a certain amount of electric potential difference.
And then disconnect the battery and remove the dielectric, and what happens?
Okay, good with that. Have a conversation.
2 equals 2.
No.
Capacitance is changing, so obviously the voltage.
No, the voltage. No,
Capacitance
the initial
changes
voltage
when
and
you
final voltage are the
insert
same.
the
The voltage of the battery.
Yeah.
So the voltage is effectively is constant as far as we're concerned. Because if you do thing, you charge it, disconnect it from the battery, put the dielectric in, reconnect it to the battery, and that's where we're at.
Right, simple. We're going to this quick one.
I'm sorry.
So the voltage is
7
change.
stretch.
My memory says 8, but I don't see how that's possible.
The voltage doubles as well.
No, you're filling the capacitance doubles.
I'm just saying mathematically.
Okay, I'm going to have to go with B.
Yeah.
Let's see.
Because the voltage shouldn't change at all because
Right.
unless we're doing something different than what we had then.
No. So the voltage, I agree completely. The voltage is determined by the battery, and you doubled that. Yep, twice the amount of energy. Okay. All right, so we're going to define this ratio of the electric field with a vacuum over the electric field with our dielectric as dielectric constant.
Okay, so
Okay, kappa. It is a specific property of a material. Okay, but it's determined by this. Okay, if the molecules polarize more easily, that means you have a higher dielectric constant, which means you have a greater field. The bigger it is, the easier it is to polarize, or the more it polarizes, the greater the field is in opposition to the induced electric field, and so it makes the total field weaker. Okay, so a vacuum has dielectric constant of 1, so that's kind of your limit.
What an insulator is the insulators. So the insulator would have one that's less than 1, or more than 1.
It would have, so this is your greatest field. This is going to be less than that, so it's going to be greater than 1.
Okay, and that is obviously 0.
Yeah.
The constant is of insulator.
Yes.
It's of the insulator that you plug in.
Yep.
So just to clarify, the E naught is before you add a dielectric and electric field, like just the E is after you add that?
Correct. Yep.
Okay, and then of a conductor is 1.
No.
No, of a vacuum is 1, and of a conductor
Of a vacuum. Mm-hmm.
Oh.
Okay. So we have. So it kind of gets to this, kind of showing the proof of this. So with a capacitance, so the new capacitance with the dielectric is equal to the capacitance with a vacuum multiplied by the dielectric constant. Okay, so on the equation sheet, I think it has this. On the AP equation sheet, I think it has this. That's the equation for capacitance. And often we're just going to use 1 unless it says you have a dielectric. But I'm pretty sure that's the equation for capacitance on the equation sheet.
Based on that at the bottom, okay. So, you mean on there, not the okay. So you mean that you're pretty sure that that's a valid equation? Sorry.
Okay. Good with that?
Yeah.
Is it normally more or less than 1?
More than 1.
More. Okay.
Less than 1. What would be something that
Good.
polarizes?
Okay. So here's I would take a picture of this if you want to reference. So this is how the dielectric constant affects, or you can use to incorporate the dielectric constant for electric field, voltage, capacitance, and energy density.
Oh, okay. And the volume's basically.
And this is for, you've charged the capacitor and then you stick you've charged the capacitor, disconnected it from the battery, and then stick the dielectric.
I see how they got H basically. I see how they got H. If that's how the energy density increases, then oh wait, no, because you're multiplying by no, it should only be never mind. No, I only saw they got H. I did that wrong.
Okay. Good with that?
Cube the energy density multiplied. Sorry.
Okay. All right. So we're looking at surface charge density. So here's our original. So this is our surface charge density of a conductor, which we expect. And then we say, well, we've got this induced charge because of the polarization. Electric fields. I wouldn't worry about that. Yeah, I don't know why I put that in there. All right. So here are some examples of different dielectrics and their constants. water is crazy surprising.
That makes sense.
It's not really surprising.
Okay.
There's a reason you don't want water anywhere near your circuits.
Okay. Good with
Is
that.
that the reason?
There's other reasons.
Okay. Oh yes. Okay. So here's our conductive plate over capacitor. Here's our dielectric. Okay. We're going to make a Gaussian surface with one end in the conductor and then the other end in the electric field. Everybody following? Remember this? Okay. So our electric field, times the area being, if this was the area being this surface here, the area being this surface here, this area, okay, is equal to the charge enclosed, which is going to be surface charge density originally minus surface charge density of our induced times our area. Tim.
Real quick.
Uh-huh.
It's an insulator,
Yeah.
the dielectric.
Uh-huh.
Wouldn't it be the more of the gas and surface we put inside of the dielectric, the more it would change?
Great question. You guys follow that question?
No.
It's like if we made this bigger or wider, isn't that including more charge? So as you do this, there's pluses and minuses. And so as you include more charge, it's just those two included charges are canceling each other out. Does that make sense?
Yeah, it's not something that's uniformly negatively charged.
Okay. But there is a point where there is more negative on one side just because there's a polarization.
You're cutting some molecules in half.
Correct. Okay. So we end up with electric field is equal to difference in the charge densities over epsilon naught. Okay. This one took me a while to digest when I was in your shoes. Okay. All right, let's use some brains. Cross the finish line running. Four questions. 10 minutes. Then you don't have to use your brain anymore.
Okay.
Yeah, because that was Spanish test, so that's like way to work.
Thumbs up when you have a guess. So this This little symbol represents ground. So you know your electric potential at this location is 0. That's all that's saying. So you know the negative plate is 0 electric potential.
Oh, that's okay. That's why you okay. So that's how the radius is right.
Tell your neighbor.
Because electric field is constant.
And D are the only two factors.
Oh, yeah. I was thinking Bradley parallel planes. Electric field is constant. It's like capacitor, right?
Yes, true.
Did I hear you say B? You're wrong.
Correct answer is?
Hey.
Correct answer is A. Okay. You have a constant electric field in between the gap. Okay. The electric potential difference is 90 volts, starts positive. So this is a higher elevation, and it goes down, and it looks like a ramp. Okay. So there we go with that. Like what the landscape looks like.
Is that negative derivative? Okay, never mind.
Yep.
That's why I was thinking.
Okay. Good with that. Yep. Negative derivative. The negative derivative of this is equal to that. Okay. This is a conductor, not an insulator. That we stick between them. Thumbs up when you have a guess. Have a conversation.
B for B.
Where are you getting the so
I'm just curious. Right. It's like. One centimeter.
Correct answer is?
B.
Correct answer is B. Beautiful babies. Okay. In my opinion, this is easier to explain. Okay. So start at 90, you have to end at 0. Through the plate, the electric potential stays the same because there is no electric field through the conductor. Okay. So it only drops here and here. Okay. This got steeper. You changed your electric potential, the same amount of electric potential in a smaller gap, which causes the electric field to be stronger. Tim.
Is that because the neutral metal slab is polarized and acts as a double capacitor, kind of.
Mm-hmm.
It acts as the
Yep.
sides of two capacitors.
Yep.
Double capacitor.
Okay, so now we stick an insulator in there rather than a conductor.
No, it's not. Oh, we have a K.
Oh, between.
Between the two things, and the small.
I got this.
Have a conversation.
Half of them are right, or half of them are
What's
wrong.
different?
Oh, it's not. Okay, there's three that's first.
Electric field is gonna be weaker inside of the
B,
thing.
B doesn't even match the
Bring on
graph.
So that knocks out
Neither
A,
does C. So B's the only way could be right.
no,
A
inside, not F.
Okay, yeah.
So then
E
you got
for E, C,
the voltage is not constant, like it's weaker.
and so the dielectric can be
So
either
C's out. And then
we don't have a theory.
B doesn't make sense because slope, negative slope. And negative 0 is not 3,000.
Mm-hmm. What?
You say this class is harder than AP.
That's totally up to you. I have not taken it.
This is literally just like if you
I mean, that's on you guys. You guys have taken it all.
the hardest class at Harrison is mythology.
Okay, we're almost done. We're almost done. We're almost done. Correct answer is E. Okay. You are. So this is definitely a process of elimination. Like I do the same thing. I should come up with better distractors. But you have a weaker field. You still have to go from 90 to 0. It's steeper in the gaps, and not so much here because the electric field is weaker. Last question. Correct answer is.
B.
I
Oh, I said B and said C.
think it's E.
Let's go. Because you know what's next to the battery?
Oh!
The charge stays the same. The voltage does not because the distance decreased. The electric field.
Double.
No, I'm just conceptually, what happens to the voltage?
So it takes
Double capacitor.
it takes less energy to go from here to here because like the charge density stayed the same. It didn't change because that's a neutral slab. It was stuck in there. It's not a charge thing. Ooh, did it? Let me chew on that a little bit.
D for double capacitor. For D for double capacitor.
Well, I mean, if the voltage doesn't have to change across the conductor, it's less
I
distance,
am
right?
It is less distance in general.
Which would decrease the voltage. But yeah, if it's inside, inside that.
Okay, what I'm trying to figure out is, did the electric field change? Initially, I'm saying I don't think it does, but I'm not 100% confident on that one. Like, I don't know if I don't think it does, because the distance away from a charged yeah, the Gauss's law though depends on this the surface charge density. I don't think it would. The devil's advocate on the other side is like, well, this polarizes. I mean, everybody's okay with that. This polarizes. Does the polarization of this in the general vicinity affect the polarization?
You can't just pull more stuff, right?
If you have charged plates, it pulls more stuff.
I know without the battery connected to it.
But why would it react back? Because in that case, you can just go on and have
That's true.
cycle where they
That's
just
true.
pull over
That's
and
true.
over and over.
I think this stays constant. So because this stays constant, there's a
It's a shorter distance.
shorter distance, and that distance is this and this, not the
The
conductor.
distance is 0.5 instead of 2.
No, the distance is 1 instead of 2. So that
There's a 1 centimeter.
1
thing in
centimeter
the
slide.
middle, and
Yeah,
they're 2
0.5.
centimeters apart.
right. So
Distance from 1.
2 minus
Oh,
1 and then
You
divided by
do
2.
it net.
yes,
You do it net.
yes,
Oh,
yeah.
I had no idea that was how that works.
So you have 0.5 here and you have 0.5
So
here.
its total is 1.
Yep.
Ooh,
I didn't know that. I was just doing it
Cray
between
cray.
plate and metal.
Got it. No, I'm looking because we know the reason why is because this is 90 volts and this is 0 volt. Oh,
That's my
no.
that was my thought too.
We know this is 0 volts
Relative. Yeah.
relative, and this
It's question mark volts.
is now half.
Right, because the distance
This
is
is-
half.
yeah.
So that,
Inside a conductor, the charge is zero.
I don't like
Or not
Yeah.
charged.
I don't like how the voltage is going to change.
I know,
Because
right?
my immediate thought process is, okay, well, voltage isn't going to change.
Right.
Because
Chart-
because it's not connected to the battery.
Correct. And the gap distance, So this is my paradigm shift through all this. Was voltage isn't about how crowded electrons are. It's about how much work it's going to take to go from one spot to the
gross.
yeah. Yes. It's not how that was a complete that has not happened. That's happened relatively recently in my pursuit of physics. Like the last 5 years, I'm like, oh.
Relatively recently. Approaching 3 minutes right now.
Okay,
Is it still recording?
it is.
It
Emma,
baffles
good
me
luck
how-
at your tennis tournament and gambling. Why do you have a basketball with a bunch of lines on it?
Topographical.
Topographic.